Alright class, now we're going to do more practice problem in a spectroscopy to make sure you get this spectroscopy down. So I gave you guys a packet with 3 problems to do. Now do me a favor, do these problems, work them out, and then watch these videos. Then you get a lot more out of it. Okay, let's do it. Let's do the first one. Here what they've given us, which I really like, they give us a formula. And we know that number of carbon times 2 plus 2 will give us the number of hydrogen we have if it was nothing but single bond. So I have 10 carbon, 10 times 2 plus 2, that would be 22 hydrogen. And it would be 22 hydrogen if I had nothing but single bond for everything. But how many hydrogen do I actually have? I have 14 hydrogen. So what does that mean? That means I am, oh my god, I do not like doing math in my head. That means I'm missing 8 hydrogen to end up with 14 hydrogen. So I'm missing 8 hydrogen. Now, remember, we said when you are missing a lot of hydrogen, number one thing that comes to mind is you probably have a benzene ring. Because benzene ring, yeah, it has a high hydrogen deficiency. Okay. Now, the other piece of information that I really like when I look at this, I go, oh, there is no oxygen, there is no nitrogen. Okay, so this is good. This is good. I've already got a lot of information out of it just by looking at the formula. Then they give you the IR absorption. These are the peaks they see on IR. And they give us hydrogen NMR. So let's go over the proton NMR and then see what we can get out of it. Ooh. The first thing I'm going to look at, I'm going to look over here. I have a peak at 7 ppm, 7.2 ppm. This is great. You know that every time you have a peak around 7 ppm, that means you have a benzene ring. And this is good because we kind of expected that just based on the formula. It's like, okay, so I know that I have a benzene ring because I have a peak at 7 ppm. Now, this peak is a mess. The best way to describe it. Now, the integration is 4 hydrogen. The integration really matters for benzene ring because you know benzene ring has 6 hydrogens. Now here you have 4 hydrogen. What does that mean? That means our benzene ring is di-substituted because otherwise it would have 6. So I have a di-substituted benzene ring. That's a good piece of information to have. Now, if you remember, if you have a di-substituted benzene ring, you could have a para, you could have ortho, or you could have meta. Which one do we have here? We know which one we don't have. There was one that I told you to look out for, and I expect you to know it, and that was para. Because when you have para, you have doublet of doublets. So I definitely don't have that. I don't have nice doublets here. I have a mess. So I know it's not para. My other options are going to be an ortho or meta. So these are my option. Okay. All right, so far so good. Now let's go to the next peak. The next peak is at 3 ppm, 3.1, 3.2 ppm. It's kind of downfield, right? But we know we don't have any oxygen or nitrogen, but we know that we have a benzene ring, which is also electron withdrawing. Okay, so that's kind of expected. So I have a peak at about 3.2 ppm. Now, when you look at the integration, it only has 1 hydrogen. That's interesting. Okay. Now, how about the pattern? The pattern is, it looks like a mess, but when we zoom in, there's a nice pattern going on. 1, 2, 3, 4, 5. I have a pentet. Okay. So I have a CH because the integration is 1. And it's a pentet. So you have probably 4 hydrogens around it. Okay, that's what I'm thinking right now. But let's move on to the next one, and we're going to come back to this. Now, the next peak is at 2.2 ppm, 2.4 ppm. Okay, this peak is also downfield. All these peaks are downfield. It's kind of interesting. Now, I know I don't have a oxygen, so I know this is not a carbon next to a carbonyl, right? Because usually when you see a peak at 2.2, you go, oh, a carbon next to a carbonyl. And we know that's not the case because we don't have an oxygen. So again, the formula really, it comes really handy. The integration is 3 hydrogen, okay? So maybe I'm looking at a CH3, and it's a singlet. So this CH3 is attached to a carbon that has absolutely no hydrogen. Okay, so that's a good piece of information. I like it so far. Now let's come to the last peak. The last peak at about 1.2 ppm. Okay, I look at the integration is 6 hydrogen. So probably I have 2 CH3s that are equivalent to each other. And look at the splitting. The splitting is a doublet. So if it's a doublet, that means the neighbor has 1 hydrogen, n plus 1 rule. The neighbor has 1 hydrogen, 1 plus 1 is 2, is a doublet. Okay? So maybe, just maybe, so I have 2 CH3s that are equivalent to each other. So 1, 2, 3, 4, 5, 6, integration of 6, and they're attached to a carbon that has only 1 hydrogen, and that's why I get a doublet. What do you guys think so far? Yeah? Okay, not bad. Now, how can we put it all together? How can we put it all together? Now, one thing I'm going to do, and I don't know why I didn't do this sooner, but I'm going to do it now. I'm going to label the peaks, A, B, C, and D. Okay? Now, if you look at peak D, these methyls that are attached to a carbon that has 1 hydrogen. Well, if you look at peak B had 1 hydrogen. So maybe this peak is this peak over here. Is that possible? Yeah, that's probably possible. Okay. Now, we also have a CH3 to count for, and this CH3 is next to a carbon that has no hydrogen. Okay. Now what I'm going to do, I want to start counting carbon. That really helps. Remember, we have 10 carbons to account for. 1, 2, 3, 4, 5, 6. 6 carbon is going to be in a ring. 7, 8, 9, 10. 7, 8, 9, 10. Okay, so I have all the carbons, 6, 7, 8, 9, 10. So I have all the pieces of information that I need. So all I have to do now is to put them together. How can I put this together? So here is, again, this is the way that, this is a part that you just play around with it. And that's what I'm going to walking you through my thought process. We're just going to play around with it and see different ways we can put these 10 pieces of carbon together. I usually teach my Chem 1 class, but I'm doing OChem, that it's kind of like playing around with Legos. You have 10 pieces of Lego. How can you put these pieces together? Let's do this. Here's what I'm thinking. So what I'm thinking is that I'm gonna have a benzene ring. And again, meta or ortho, I'm not expecting you to know that right now. So this is the ugly benzene ring. Let me draw a pretty benzene ring. So I'm not expecting to know that right now, so don't worry about that part. I'm just going to expect it is to be ortho. Doesn't matter right now. So I know I have a methyl. I have a CH3 here. That's one piece I have. And the other piece I have a CH that is attached to a methyl and attached to a methyl. Would this work out? I think so. So let's go over to make sure this works out. So these are our D hydrogen, and yeah, makes sense. Then it has only one neighbor, it's a CH. 1 plus 1 rule is a doublet. That's what we get. We got a doublet here. 1, 2, 3, 4, 5, 6. Integration matches up nicely. This one over here is just a methyl, is a singlet. So it has to be next to a carbon that has no hydrogen. Okay, could this be just attached to the benzene ring? Yeah. And if I had a CH3 that was not attached to a benzene ring, it would probably be more up field. It will be probably around 1 ppm. But this one about 2 ppm, and it's because it's directly attached to the benzene ring. So this makes sense. That's good. Now, peak B would be my CH over here. Okay, so one integration CH, that sounds good. Again, it's downfield-ish, right? Because it's around after 3 ppm, because it's directly attached to a benzene ring. So that's acceptable. I can buy that. Now, look at this splitting. At the beginning, I thought it was like a pentate, right? I go 1, 2, 3, 4, 5. But you can see the other ones are coming out over here too, right? And what type of splitting would you expect for this? On this side, it has no hydrogen. On this side, it has 1, 2, 3, 4, 5, 6. And since these two are equivalent to each other, this is key. Pay attention to this one. So let's go over this one more time. From this carbon, it has no hydrogen. From the other side of the neighboring, it has 2 CH3s. These two are equivalent to each other. Because these two are equivalent to each other, they're going to be additive. So the N+1 rule here, it would be 6 plus 1, which is 7. So I accept a heptade over here. And if you really look over here, that's actually what we see. You see the one right here? 1, 2, 3, 4, 5, 6, 7. It's really hard to see once it's past a quartet, but you can actually see, yeah, this does have the 7 peaks that we're looking for. Yeah, okay. So I feel pretty good about that. Now, what are going to be my A? Okay, there's a hydrogen here, hydrogen here, hydrogen here, and hydrogen here, and all those are overlapping. That's where I get a big mess over here. These are all overlapping, and that's what I get a big mess in this region. Yeah, this is pretty reasonable. Yeah, I'm pretty happy with this. Again, is it ortho or meta? That's not what I'm expecting. I would accept both at this point. All right, I feel good about this. Ready to do the next one? Let's do the next one. Here is the next one. I have the formula. I do like the formula. Number of carbon is 9. 9 times 2 plus 2. That would be 20 hydrogen. Again, and it's 20 hydrogen if I had nothing but all single bond. But how many hydrogen do I actually have? I have only 9 hydrogen, right? So I only have 9 hydrogen. So how am I? I'm missing 11 hydrogen. So a lot of hydrogen. Did I do the math right? I think I did. Which gives me 9 hydrogen. Okay. So again, 9 times 2 plus 2, that would be 20. But I'm missing 11 hydrogen because I only have 9 hydrogen. Now, when I look at this, I go, oh my God, I'm missing a lot of hydrogen. And when I'm missing a lot of hydrogen, the first thing I usually think about is like, benzene ring sounds about right now. All right. So also there's no oxygen, there's no hydrogen. This is good. This is giving me a lot of information. Use that formula. These are, I give you carbon-13 signals. That's interesting. We're not going to do any carbon-13 in this class, so you can ignore it for now. Now, I'm going to come over here to Proton Nmr. This is very interesting. It's very interesting because I only have 2 peaks. All that carbon, I only have 2 peaks. And both my peaks are singlet. What is this compound? Let's analyze the 2 singlet peaks that we have. I look at this one and I go, okay, I know it's a benzene ring because it's around 7 ppm. I know it's a benzene ring, 7 ppm. And the integration is 3 hydrogen. So benzene ring would have 6 hydrogen. I only have 3 hydrogen. I'm missing 3 hydrogen. So it's a tri-substituted benzene ring. That's good to know, right? Tri-substituted benzene ring. Okay. Now I'm going to come over here and I have 9 hydrogen, right? When I go 9 hydrogen, the one thing I can think about is probably I have 3 methyls that are equivalent to each other and are next to a carbon that has no hydrogen. Now, the last problem we did, these two methyls were attached to the same carbon. Do you think these three methyls are going to be attached to the same carbon? Do you think they are going to be all attached to the same carbon? And then this carbon would have no hydrogen? Well, possible, right? It's not impossible. But when I look at this, I have 9 hydrogen, right? So this has 6 hydrogen. And 1, 2, 3, this has 3 hydrogen. 6 plus 3 is 9. So I'm already accounted for every single carbon I need. So carbons do not grow on trees, right? I can't just make up carbon number 10. Again, I want to take a step back just to make sure you follow what I said. I said 1, 2, 3, 4, 5, 6, 7, 8, 9. So I already have 9 carbon. I don't really need this carbon, right? So I want to say that's not a possibility. So I'm actually going to take that away. So I have already accounted. So this was 6 carbon. This was 3 carbon. So I have 9 carbon. Count your carbons many, 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 many times. I always do it because it helps to count your carbons all many times. Okay, so probably those carbon are directly attached to a benzene ring because then that carbon would have no hydrogen. Because again, there's no other options we have. And then this is about 2.2 ppm, so it's a little bit more downfield. So again, if you are directly attached to a benzene ring, you know that you're going to be more downfield. You know it from last problem, right? This CH3 was about 2.2 ppm. So every time I have a 2.2 ppm, the first thing I think about next to a carbonyl, but I have no oxygen. And the second thing I think about, okay, is directly attached to a benzene ring. All right, how can we put this together? This is tricky. So I have all the pieces. You have all the pieces. 3 CH3s and then 1 benzene ring. How we are going to put this together? How many different ways? This is tricky. Now, how about this? So I know I need to have a tri-substituted benzene ring. And it's a singlet. So there is like symmetry going all around it. What if I do this? Let me actually draw the CH3s. What do you guys think of that? Yeah? I think we got it, right? So these are my B peak, and they're all equivalent to each other because there's so much symmetry going on in this compound, and they're all attached to a carbon that has no hydrogen, so they are singlet, okay? And they all are in the exactly same environment because there's so much symmetry going on here. So they're all equivalent to each other. Now, let's go for peak A. So for peak A, there will be a hydrogen here, and hydrogen here. And if you see, these hydrogen will also be exactly equivalent to each other because this hydrogen is sandwiched between 2 carbon, and each of those have a methyl. This hydrogen sandwiched between 2 carbon, each one have a methyl. This hydrogen sandwiched between 2 carbon, and each one has a methyl. So yeah, there is so much symmetry going on. What do you think? I think we got it down. I felt pretty good about this structure. This was a tricky one. This one is a tricky one. And when I see a lot of singlet and all that, I usually think about symmetry. Are there a lot of symmetry going on in this compound? All right. And the other thing to help you really undo these problems is to remember that count your carbon. You should always count your carbon many times. I'm going to do it one more time here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. Even count your hydrogen, even though you're so short about. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogen. That's good. All right. Before we do the last one, the other thing I want to reiterate one more time is that we knew we had no oxygen here. And when I have a peak at 2.2 ppm, it's likely that you have carbon that is directly attached to a benzene ring. We saw it over here, and we're seeing it here right now. Okay. Let's do the last one. All right, here is our last one. Again, ooh, I like this. I think I've shown you so far that you really can get far with the formula. So 8 times 2 plus 2, that is, oh my goodness, I don't like doing math in my head. 18 hydrogen, yeah? That sounds about right. Okay, so our number of hydrogen, we have 8 hydrogen, 8 times 2 plus 2, that's 18, if everything was single bond. If we had nothing but single bond. But how many hydrogen do we actually have? We actually have 10 hydrogen, okay? We actually have 10 hydrogen, so we are missing 8 hydrogen. We're missing 8 hydrogen to end up getting 10 hydrogen. So I'm missing 8 hydrogen. Again, every time I'm missing 8 hydrogen, I'm missing a lot of hydrogen. The first thing that I think about, I go, benzene ring sounds pretty good, right? There's some IR here. I know I have no oxygen. That's good. I know I'm missing a lot of hydrogen. Now I'm going to go to Proton Nmr. Proton Nmr, I'm going to look over here. Okay, around 7 ppm, I have a peak. That's good. That means I probably have a benzene ring. And that's really good because it kind of confirms what I knew based on the formula. All right, I have a benzene ring at about 7 ppm. The integration is 5 hydrogen. Okay, so if the integration is 5 hydrogen, I have a mono-substituted benzene ring because it's just missing 1 hydrogen. That makes my job easier because then there is no para, ortho, and meta I have to worry about. So I have a mono-substituted benzene ring. Okay. When I look at the next peak is around, it's kind of downfield, 2.7, 2.8 ppm. That's interesting. And then it has 2 hydrogen, okay? So maybe I'm looking for a CH2. And then what's the splitting? The splitting, this one is nicely, you can tell. 1, 2, 3, 4. This one is a quartet. This one I'm kind of sure about. All right, so I have a CH2. It's a quartet, so it's probably attached to a CH3, right? Because again, n plus 1 rule, I have 3 plus 1, 4. I get a nice quartet here. I feel pretty good about this right now. I'm going to come over here. I have a bad peak about 1.2, 1.3 ppm. And then this peak has 3 hydrogen. So maybe I'm looking at a CH3. Now, when you look at this peak, the splitting is a very nice triplet. If you have a really nice triplet, most likely, what is the neighbor? The neighbor is a CH2, right? N plus 1 rule. So probably the neighbor has a 2 hydrogen. 2 plus 1 would be 3. I get a nice triplet. All right. Well, that's interesting, isn't it? Because let me label the peaks. I always keep forgetting to do that. Let me label the peaks. So peak B, we know we had a CH2 possibly attached to a CH3 because it was a quartet. And peak C, we have a CH3 that we think is attached to a CH2 since we have a triplet. Well, probably these are the same thing, right? Probably these are the same thing. So this is probably C and this is probably my B. So I have one piece over there. Now what I'm going to do, I'm going to count carbon because counting carbon is good. Counting carbon really, really helps. So here I have 6 carbon and here I have 2 carbon. So together I have 8 carbon. That's good. So all the carbons are accounted for. So I have a benzene ring and I have this piece and that will account for all the carbons. So I have 2 pieces to put together. That's not bad. Also, is a mono-substituted benzene ring. So there are not that many ways I can actually put this together. The only way that I can think about. So here is my benzene ring. I need to practice drawing these things on an iPad. Here is my benzene ring, okay? And I know it's mono-substituted and a CH2, CH3 is the only other piece of the puzzle that I have. Yeah, not bad. So here again, this would be my peak C, this would be my peak B, and these are all peak A. They're all overlapping with each other, right? They're all kind of overlapping with each other. That's why I get a big mess over here. I feel pretty good. 5 hydrogen over here at 7 ppm. This is CH2 directly attached to a benzene ring. That's why it's kind of downfield. We've been seeing that over and over again. When you're directly attached to a benzene ring, you become a little bit more downfield. I have that. On this side, it has no hydrogen. On the other side, it has 3 plus 1 quartet. I have a quartet. I come over here, it has nothing on this side, of course. It has a CH2 here, 2 plus 1, triplet. I have a triplet. Then I feel pretty good about this one. All right, nice job. This was a good study session. Okay, thanks for hanging in there with me. I will talk to you guys next time.